Imagine a time before time itself was measured, a period in cosmic history when the universe was a chaotic expanse of gas, dust, and invisible forces. Approximately 4.6 billion years ago, in a relatively quiet corner of the Milky Way galaxy, an enormous molecular cloud, mostly hydrogen and helium, was drifting through space. This cloud, composed of the remnants of previous generations of stars, was silent but filled with potential energy. The story of our Sun begins here, in this seemingly ordinary cloud that would eventually become the luminous heart of our solar system. Gravity, the silent architect of the universe, began its subtle work. Slight variations in density within the cloud caused certain regions to attract more matter, slowly growing in mass and density. As particles collided, friction generated heat, and the cloud began to contract. This process, known as gravitational collapse, is the fundamental mechanism behind star formation, a delicate balance between gravity pulling inward and pressure pushing outward. In these early moments, the core of what would become the Sun reached temperatures high enough to ignite nuclear fusion. The first reactions involved hydrogen atoms fusing into helium, releasing immense amounts of energy. This energy, radiating outward, would eventually become the light and warmth that sustain life on Earth. But in the beginning, it was a chaotic furnace, a protostar shrouded in gas and dust, invisible to distant observers except for faint infrared emissions detectable by the most sensitive instruments. Scientists today, using advanced telescopes like the Hubble Space Telescope and data from observatories like ALMA, can witness similar star-forming regions in our galaxy. Nebulae, such as the Orion Nebula, show us clouds of gas and dust where stars are being born right now. These observations provide a window into the same processes that formed our Sun billions of years ago, allowing us to reconstruct the past with remarkable accuracy. The Sun's formation was not an isolated event. Surrounding it was a spinning disk of gas and dust, gradually coalescing into planets, moons, asteroids, and comets, a protoplanetary disk. This disk was critical, as it would determine the architecture of our solar system, the positions of planets, and their composition. The inner regions, hotter and denser, eventually formed rocky planets like Mercury, Venus, Earth, and Mars, while the outer cooler regions became gas giants like Jupiter and Saturn. During its infancy, the Sun was a highly active star, experiencing intense solar winds and frequent eruptions of plasma. These solar flares shaped the environment of the early solar system, stripping lighter elements from nearby forming planets and influencing the chemical composition of asteroids and comets. The Sun's magnetic field, still in formation, played a crucial role in protecting the emerging planets from high-energy cosmic radiation. The creation of the Sun is also a story of time and patience on a cosmic scale. While the formation process may seem sudden in human terms, it unfolded over tens of millions of years, a relatively brief moment in the universe's lifespan. Each stage, from the initial collapse to the ignition of nuclear fusion, represents a finely tuned sequence of events, governed by physics, yet seemingly orchestrated with cosmic precision. Understanding the Sun's birth is not just an exercise in astronomy. It is a journey into our own origins. The elements within our body's carbon, nitrogen, oxygen, were forged in earlier generations of stars, recycled through supernova, and finally incorporated into the molecular cloud that became our Sun. In essence, by studying the Sun's creation, we study the origins of life itself, the material and energy that made Earth habitable, and the processes that shaped the delicate balance of our solar system. As researchers continue to model the Sun's early development, they use computer simulations that replicate the dynamics of gas and dust under the influence of gravity and thermonuclear reactions. These simulations confirm that even small variations in density and temperature could have significantly altered the outcome, potentially leading to a completely different solar system. Such insights underscore the extraordinary precision required for our Sun and, by extension, Earth to exist as it does. The Sun's birth is not merely a historical event. It is an ongoing influence. The balance it struck billions of years ago, the way it stabilized and maintained nuclear fusion in its core, continues to sustain life on Earth today. From its formation to the present, the Sun exemplifies the extraordinary power and elegance of stellar physics. A beacon of light arising from the depths of cosmic darkness. The Sun, our life-giving star, is far more than a glowing ball of fire. Beneath its serene, radiant surface lies a complex and dynamic structure, a masterpiece of cosmic engineering that has fascinated scientists for centuries. To understand the Sun is to understand the very engine that drives our solar system, the star that has sustained life on Earth for billions of years. At the heart of the Sun lies the core, the central powerhouse where nuclear fusion occurs. In this extreme environment, temperatures soar to approximately 15 million degrees Celsius, and pressures reach over 250 billion times the atmospheric pressure on Earth. Within this intense crucible, hydrogen nuclei collide and fuse to form helium, releasing vast amounts of energy in the form of gamma rays. These reactions are governed by the principles of quantum mechanics and nuclear physics, and they are remarkably efficient, converting only a fraction of the Sun's mass into energy, yet generating enough to power the entire solar system. Surrounding the core is the radiative zone, a region extending outward about 70% of the Sun's radius. Here, energy travels slowly from the core toward the surface, a journey that can take hundreds of thousands of years. Photons produced in the core are absorbed and re-emitted countless times, gradually diffusing outward in a process that resembles a cosmic pinball game. Despite the slow pace, this zone plays a crucial role in regulating the flow of energy and maintaining the Sun's stability. Above the radiative zone lies the convective zone, a turbulent layer where heat is transported by the movement of hot plasma. Massive convection currents rise and fall, carrying energy toward the Sun's surface. This churning motion is responsible for many of the Sun's surface phenomena, including sunspots, solar flares, and prominences. The convective motions also interact with the Sun's magnetic field, twisting and tangling magnetic lines of force, which can store energy and release it explosively, influencing space weather throughout the solar system. The Sun's visible surface, known as the photosphere, emits the light that illuminates our world, although it appears calm and uniform from a distance. Closer examination reveals granules and sunspots, regions of intense magnetic activity that are cooler than their surroundings. Sunspots, first observed through early telescopes in the 17th century, are manifestations of the Sun's magnetic complexity and provide clues about solar cycles and the long-term behavior of our star. Above the photosphere lies the chromosphere, a thin layer of glowing gases that is more easily seen during solar eclipses as a reddish ring encircling the Sun. The chromosphere is a region of intense activity, where temperatures rise from 4,500 degrees Celsius at its base to tens of thousands of degrees at its top. This dramatic increase is still a subject of active research, challenging our understanding of energy transport in stellar atmospheres. Far beyond the chromosphere extends the corona, the Sun's outermost layer, which stretches millions of kilometers into space. Surprisingly, the corona is far hotter than the layers beneath it, with temperatures exceeding 1 million degrees Celsius. This counterintuitive phenomenon, known as the coronal heating problem, has puzzled astronomers for decades. Scientists believe that magnetic reconnection, waves, and other plasma processes contribute to heating this tenuous outer layer. The corona is also the source of the solar wind, a stream of charged particles that flows outward through the solar system, shaping planetary magnetospheres and influencing space weather on Earth. The Sun's magnetic field is a critical component of its structure, driving sunspots, solar flares, and coronal mass ejections, generated by the motion of conductive plasma in the convective zone. This dynamo effect produces a complex and ever-changing magnetic environment. The Sun's magnetic cycles, roughly 11 years in duration, modulate solar activity and can have profound effects on Earth, including geomagnetic storms that disrupt satellites and power grids. Modern science relies on sophisticated instruments to study the Sun's structure. Satellites, such as the Solar and Heliospheric Observatory, SOHO, the Parker Solar Probe, and the Daniel K. Inouye Solar Telescope, provide unprecedented insights into the Sun's inner workings. Helioseismology, the study of waves propagating through the Sun, allows scientists to infer internal structures with remarkable precision, revealing variations in density, temperature, and rotation that would otherwise be hidden from view. Understanding the Sun's structure is not merely an academic pursuit. It is essential for predicting space weather, assessing the Sun's long-term stability, and safeguarding life on Earth. From the fusion reactions in the core to the magnetic storms in the corona, the Sun is a dynamic, interconnected system, a testament to the power and complexity of stellar physics. The Sun, the brilliant star at the center of our solar system, owes its incredible energy to a process that defies the imagination of everyday experience: nuclear fusion. This invisible furnace, buried deep within the Sun's core, is the source of the light and heat that makes life on Earth possible. Without it, our planet would be a frozen, lifeless rock drifting in darkness. Understanding the Sun's fuel is not only essential to astronomy, but also provides insights into the fundamental laws of physics that govern the universe. At the heart of the Sun, hydrogen atoms collide at unimaginable speeds under extreme temperature and pressure conditions. In this core, where temperatures soar to around 15 million degrees Celsius and pressures reach 250 billion times that of Earth's atmosphere, hydrogen nuclei overcome their natural electrical repulsion. They fuse together to form helium nuclei in a process known as the proton-proton chain reaction, releasing vast amounts of energy in the form of gamma-ray photons. This reaction converts a tiny fraction of mass into energy, demonstrating Einstein's iconic equation, E equals mc, in action. But the journey of energy from the Sun's core to its surface is a complex, time-consuming odyssey. Photons generated in the core do not escape immediately. They enter the radiative zone, where they are repeatedly absorbed and re-emitted by ions, taking perhaps hundreds of thousands of years to slowly work their way outward. This painstaking process ensures the sun's energy is gradually released, maintaining a delicate balance that stabilizes the star. Beyond the radiative zone, in the convective zone, hot plasma rises and cooler plasma sinks in immense convection currents. These turbulent movements help transport energy closer to the Sun's surface and play a critical role in the Sun's magnetic dynamo. The convective motions, interacting with magnetic fields, create the familiar patterns of sunspots and solar flares, visible indicators of the enormous energy generated deep within. The Sun's energy output is staggering. Every second, the Sun converts approximately 600 million tons of hydrogen into 596 million tons of helium, releasing 4 million tons of energy in the form of photons and neutrinos. This energy radiates outward, eventually reaching Earth as sunlight, nourishing plants, warming the atmosphere, and driving the water cycle. The scale is almost impossible to comprehend. The Sun emits more energy in 1 second than all human civilization has consumed in its entire history. Neutrinos, nearly massless particles produced during nuclear fusion, escape the Sun's core almost instantaneously, carrying information about the fusion processes taking place. Detection of these solar neutrinos on Earth, using massive underground detectors like the Sudbury Neutrino Observatory in Canada, has confirmed theories about the Sun's energy production and provided evidence for neutrino oscillation, a remarkable phenomenon in particle physics. The nuclear fusion process that powers the Sun is self-regulating. If the core temperature were to rise slightly, fusion rates would increase, causing the core to expand and cool, restoring equilibrium. Conversely, if the core cooled, fusion would slow, contraction would occur, and temperatures would rise. This remarkable stability has allowed the Sun to shine steadily for approximately 4.6 billion years and promises another 5 billion years of relatively stable energy output. The Sun's fuel is not infinite. Hydrogen in the core will eventually deplete, and the Sun will transition into a red giant phase, expanding to engulf the inner planets and radically transforming the solar system. However, for the present, the fusion of hydrogen into helium continues, a relentless, efficient, and awe-inspiring process that sustains the life-giving energy we depend on. Observations of other stars at different stages of their life cycles provide valuable context. Young stars, rich in hydrogen, burn brightly with intense energy, while older stars that have exhausted their core fuel expand and cool, eventually shedding outer layers and leaving behind dense remnants such as white dwarfs. By studying these stellar analogs, astronomers can infer the Sun's past behavior and predict its future evolution, deepening our understanding of stellar physics and cosmic history. The energy produced in the Sun's core is also responsible for driving the heliosphere, a vast bubble of charged particles extending beyond Pluto, which shields the solar system from cosmic rays and interstellar material. Without this protective bubble, life on Earth and the stability of planetary atmospheres could be drastically different. In this sense, the Sun's fuel is not just the source of light and warmth, it is the guardian of the solar system's very structure. As the Sun settled into a steady rhythm of nuclear fusion, the surrounding protoplanetary disk composed of gas, dust, and cosmic debris began to undergo a remarkable transformation. Within this disk, subtle variations in density and temperature initiated a process that would give rise to the first planet, a world formed from the primordial remnants of stellar creation. This was not an overnight event. It was a story that unfolded over millions of years, a cosmic ballet of collisions, accretion, and gravitational forces shaping the foundation of the solar system. Scientists believe that the first planet to emerge was likely a small, rocky body in the inner regions of the solar system, where temperatures were high enough to prevent volatile compounds like water and methane from condensing. These inner regions, known as the terrestrial zone, were dominated by silicate minerals and metals essential building blocks for the earliest planetary cores. Over time, countless tiny particles, dust, grains, and pebbles collided and stuck together through a process called accretion, gradually forming larger planetesimals. The growth of these planetesimals was a violent and chaotic process. Collisions released enormous amounts of energy, melting surfaces and triggering differentiation, the separation of dense materials like iron and nickel toward the core, and lighter silicates toward the mantle and crust. This internal differentiation created the structural foundation necessary for a planet to evolve geologically, with a dense metallic core, a rocky mantle, and eventually a stable crust capable of supporting future geological activity. Gravity played a decisive role in the emergence of the first planet. As the largest planetesimals gained mass, their gravitational influence increased, allowing them to attract additional material and accelerate growth. This runaway accretion ensured that a single body could dominate its local region of the disk, sweeping up smaller fragments and clearing its orbit, a hallmark of true planetary formation. In addition to accretion, the young planet experienced intense bombardment by leftover debris, a period known as the Late Heavy Bombardment, which shaped its surface and contributed to the delivery of essential elements such as water and carbon compounds. These impacts left deep craters and influenced the planet's early geological activity, creating the initial conditions for volcanic activity and tectonic movements. The first planet's orbit was not static. Interactions with other forming planets and with the Sun's gravitational pull created subtle shifts, eccentricities, and inclinations, gradually stabilizing over millions of years. This delicate balance allowed the planet to maintain a consistent distance from the Sun, a crucial factor in determining its surface temperature, potential atmosphere, and long-term evolution. Observations of exoplanetary systems in our galaxy provide compelling parallels to this early stage of planetary formation. By studying young star systems with protoplanetary disks, astronomers witness similar processes of accretion, differentiation, and orbital evolution. These observations confirm that the formation of planets is a universal process, governed by the same physical laws that shaped our solar system. The composition of the first planet was predominantly silicate rock and metals, with traces of other elements delivered by impacting asteroids and comets. Its surface, initially molten due to heat from accretion and radioactive decay, gradually solidified to form a primitive crust. Volcanoes spewed molten rock and gases, gradually releasing an early atmosphere composed mainly of carbon dioxide, nitrogen, and water vapor, an environment far removed from the breathable air we know today. Yet the first step toward planetary habitability, the first planet's magnetic field, generated by the motion of molten metals in its core, provided a rudimentary shield against solar radiation and charged particles. This magnetic protection was essential in preventing the complete stripping of its early atmosphere by solar winds, and contributed to the long-term stability of the planet's environment. Studying this first planet allows scientists to understand the blueprint for terrestrial planet formation. Mercury, the innermost planet of our solar system, is often considered a modern analog due to its small size, dense core, and proximity to the Sun. By analyzing Mercury's composition, crater record, and magnetic field, researchers reconstruct the conditions that likely prevailed when the first planet emerged billions of years ago. The formation of the first planet was more than the creation of a celestial body. It was the beginning of a complex planetary ecosystem that would eventually include Earth, Mars, and other inner worlds. Its existence influenced the distribution of material in the solar system, shaped the trajectories of other forming planets, and established the initial conditions necessary for the diversity of worlds that followed. The inner region of the solar system, bathed in the radiant energy of the young sun, became the cradle for the terrestrial planets: Mercury, Venus, Earth, and Mars. These rocky worlds, each with a unique composition and geological history, share common origins, yet diverge in fascinating ways. Their formation is a tale of cosmic collisions, differentiation, and environmental evolution that shaped the foundation for everything from planetary atmospheres to the potential for life. Following the emergence of the first planet, the remaining material in the inner protoplanetary disk continued to accrete. Gravity dictated the fate of dust, pebbles, and planetesimals, gathering them into progressively larger bodies. Within this chaotic environment, Mercury formed closest to the Sun, enduring intense heat and bombardment. Its small size and proximity meant that it lost much of its lighter elements, leaving a dense, iron-rich core that makes up nearly 85% of its radius. Mercury's surface, heavily cratered and scarred, tells a story of relentless cosmic impacts during the early solar system, and its weak magnetic field hints at a partially active core even today. Further out, Venus and Earth developed under similar conditions, but with crucial differences in mass and distance from the Sun. Venus, with its slightly smaller size than Earth, accumulated a thick atmosphere dominated by carbon dioxide, resulting in a runaway greenhouse effect. Surface temperatures soared, creating an environment inhospitable to life as we know it. Geological activity continued for billions of years, evidenced by massive volcanoes and tectonic features, but the lack of water prevented the stabilization of a habitable surface. Earth, positioned at the optimal distance from the Sun, became a unique terrestrial planet capable of supporting life. The process of differentiation produced a layered structure, a dense metallic core, a viscous mantle, and a solid crust. The core's rotation generated a magnetic field that protected the atmosphere from solar wind erosion, while volcanic outgassing contributed to the formation of the early atmosphere, rich in carbon dioxide, water vapor, and nitrogen. The bombardment of icy comets and water-rich asteroids delivered essential volatiles, seeding the planet with oceans. The combination of liquid water, a stable climate, and energy from the Sun set the stage for the emergence of life, making Earth a singular jewel in the inner solar system. Mars, the outermost of the terrestrial planets, provides a contrasting example of planetary evolution. Slightly smaller than Earth, Mars lost much of its internal heat more quickly, leading to a cessation of significant tectonic activity. Its atmosphere, primarily carbon dioxide, thinned over time due to solar wind stripping, and surface water became largely locked in polar ice caps and subterranean reservoirs. Despite its present-day aridity, ancient river valleys, deltas, and mineral deposits reveal a past where liquid water flowed abundantly, suggesting that Mars once held conditions favorable for life. The interplay between these terrestrial planets and the Sun's early activity cannot be overstated. Intense solar radiation, frequent flares, and solar wind sculpted planetary surfaces, eroded atmospheres, and influenced magnetic field development. Each planet's unique mass, composition, and distance from the Sun determined how it withstood these challenges, resulting in the diverse planetary environments we observe today. Modern research into terrestrial planets relies heavily on data from spacecraft and telescopes. Mercury was explored by NASA's MESSENGER mission, providing unprecedented detail on its surface and magnetic field. Venus has been studied by missions such as ESAS, Venus Express, and JXAS Akosky, revealing insights into its thick atmosphere and volcanic activity. Mars, of course, has been extensively investigated by orbiters, landers, and rovers, including NASA's Perseverance and Curiosity missions, uncovering evidence of past water, climate history, and the planet's geological evolution. Earth remains our reference point, studied from orbiting satellites to deep drilling projects, offering the most comprehensive understanding of terrestrial planet processes. The terrestrial planets also offer a laboratory for understanding planetary habitability. By comparing their differences, Earth's life-supporting environment versus Venus's scorching greenhouse and Mars's desiccated landscapes, scientists can explore the delicate balance of factors required for life. This comparative planetology informs the search for exoplanets, guiding astronomers to identify potentially habitable worlds around distant stars. In essence, the terrestrial planets are the building blocks of our solar system's inner region, each a testament to the complex interplay of physics, chemistry, and cosmic timing. Their surfaces, atmospheres, magnetic fields, and geological histories provide a rich tapestry that reveals the processes that transformed a disk of dust and gas into dynamic, differentiated worlds capable of hosting diverse environments. Mars, the enigmatic red planet, has captivated human imagination for centuries. Its ruddy surface, visible even to the naked eye, inspired ancient astronomers to name it after the Roman god of war. Yet beyond its striking appearance lies a world with a complex history, shaped by cataclysmic impacts, volcanic activity, and evidence of liquid water that hints at the possibility of past life. To understand Mars is to peer into a planetary laboratory, a natural archive that records billions of years of solar system evolution. Mars formed approximately 4.6 billion years ago in the outer reaches of the terrestrial zone, where temperatures were cooler than those near Venus or Earth. Its smaller mass compared to Earth meant that it lost heat more rapidly, causing its core to cool and its internal dynamo to weaken over time. Despite this, early Mars likely possessed a magnetic field capable of shielding its atmosphere from the intense solar wind. This magnetic protection, though temporary, played a pivotal role in preserving a thicker early atmosphere and creating conditions suitable for liquid water on the surface. The planet's geological history is written across its surface. Olympus Mons, the tallest volcano in the solar system, rises nearly 22 kilometers above the surrounding plains, evidence of prolonged volcanic activity. Vast canyon systems, such as Valles Marineris, stretch thousands of kilometers, carved by tectonic stresses and potentially by flowing water. Ancient river valleys, delta formations, and mineral deposits reveal that water once flowed abundantly, creating lakes, rivers, and possibly shallow seas. These features suggest that Mars, at one time, may have had a climate capable of supporting microbial life. Mars' reddish hue originates from iron oxide or rust coating much of its surface. Dust storms frequently sweep across the planet, sometimes enveloping it entirely, a testament to its thin but dynamic atmosphere. These storms, driven by temperature differences and solar heating, shape the landscape, redistribute surface material, and provide challenges for exploration missions. The search for water and past life has driven decades of Mars exploration. NASA's rovers, including Spirit, Opportunity, Curiosity, and Perseverance, have examined rocks, soil, and atmospheric conditions. They have uncovered sedimentary layers, hydrated minerals, and complex organic molecules, providing compelling evidence that liquid water once existed and that Mars had a more hospitable environment in its ancient past. Additionally, orbiters such as Mars Reconnaissance Orbiter and ESA's Mars Express have mapped the planet in remarkable detail, revealing the extent of polar ice caps, canyon networks, and volcanic plains. The planet's climate history is equally fascinating. Mars likely experienced a warmer, wetter era billions of years ago, followed by a gradual cooling and thinning of the atmosphere. Today, the planet has a tenuous atmosphere composed mostly of carbon dioxide, with surface pressures less than 1% of Earth's. The loss of atmosphere is attributed to a combination of solar wind stripping, insufficient magnetic shielding, and the planet's reduced gravity. Despite its current aridity, signs of past glacial activity and the presence of subsurface ice suggest that water remains locked within Mars' crust and polar regions. Mars exploration is not limited to understanding its past. It is central to humanity's quest for interplanetary settlement. Scientists study its soil, radiation levels, and seasonal cycles to prepare for potential human missions. Understanding Mars' environment, resource utilization, and long-term habitation possibilities, making it both a scientific and strategic priority for agencies like NASA, ESA, and private ventures such as SpaceX. Moreover, Mars offers a comparative lens to study Earth, its geological features, climate shifts, and potential for life help scientists test theories about planetary evolution, atmospheric loss, and habitability. By examining why Mars transformed from a wetter world to the dry, cold planet we see today, researchers gain insights into Earth's resilience and the delicate balance that sustains life here. The red planet remains a tantalizing mystery. Its frozen poles, dust-laden landscapes, and remnants of ancient rivers tell a story of change, survival, and the potential for discovery. Each rover mission, each orbital survey, brings humanity closer to answering profound questions. Did life ever exist on Mars? Could humans one day thrive there? And what does Mars teach us about the nature of planets in our galaxy? Jupiter, the colossal gas giant, stands as the sovereign of our solar system, a planet whose sheer size and power dwarf all other worlds. With a mass more than twice that of all the other planets combined, Jupiter is a swirling behemoth of hydrogen and helium, a living laboratory of extreme physics, meteorology, and magnetism. Understanding Jupiter is essential for comprehending the formation, evolution, and architecture of the entire solar system. Jupiter formed approximately 4.5 billion years ago in the colder outer regions of the protoplanetary disk. Its massive gravitational pull allowed it to accrete vast quantities of gas before the solar wind expelled much of the remaining material. Unlike terrestrial planets, Jupiter did not develop a solid surface in the conventional sense. Rather, it consists of layers of gas transitioning gradually into liquid and metallic hydrogen as pressure increases toward its core. This unique composition makes Jupiter both enigmatic and awe-inspiring. At its heart, Jupiter is believed to harbor a dense core, possibly composed of rock, metal, and ice, surrounded by a thick envelope of metallic hydrogen. Under pressures exceeding 40 million times Earth's atmosphere, hydrogen behaves as an electrical conductor, generating one of the most powerful magnetic fields in the solar system. This magnetic field, extending millions of kilometers into space, traps charged particles, forms intense radiation belts, and interacts with the solar wind, creating spectacular auroras at Jupiter's poles. Jupiter's atmosphere is a dynamic and turbulent realm. Dominated by hydrogen and helium, it also contains trace amounts of methane, ammonia, and water vapor, which play critical roles in cloud formation and weather patterns. The planet is renowned for its vivid bands, the colorful belts and zones that encircle the planet in alternating patterns. These bands are created by high-speed windsome exceeding 600 kilometers per hour, moving in opposite directions, producing shearing effects and dramatic turbulence. Perhaps the most iconic feature of Jupiter is the Great Red Spot, a colossal storm that has raged for at least 400 years, possibly much longer. This anticyclonic tempest is larger than Earth itself, a swirling vortex of hypershear gases, whose reddish hues result from complex chemical reactions influenced by sunlight and the planet's atmospheric composition. The Great Red Spot exemplifies the immense energy, scale, and longevity of weather systems on Jupiter, a planet that is never still. Jupiter's influence extends far beyond its gaseous envelope. Its strong gravitational field has played a pivotal role in shaping the solar system. By acting as a cosmic shield, Jupiter deflects or captures many comets and asteroids that might otherwise impact the inner planets, including Earth. Conversely, its gravity has also perturbed objects in the asteroid belt, influencing planetary formation, and in some cases, sending celestial bodies on collision courses with other planets. Jupiter is accompanied by an extensive system of moons, over 95 identified to date, ranging from tiny, irregular satellites to the massive Galilean moons, Io, Europa, Ganymede, and Callisto. Each moon presents a unique environment and geological story. Io is the most volcanically active body in the solar system, its surface continuously reshaped by tidal heating from Jupiter's immense gravity. Europa's icy crust conceals a subsurface ocean, making it one of the prime candidates for extraterrestrial life. Ganymede, the largest moon in the solar system, possesses its own magnetic field, and Callisto's heavily cratered surface records billions of years of impacts. Jupiter's moons are more than companions. They are miniature worlds that provide insights into planetary processes and the potential for life beyond Earth. Modern exploration has unveiled Jupiter's majesty in unprecedented detail. NASA's Juno spacecraft, orbiting the planet since 2016, has mapped its gravity, magnetic fields, and atmospheric dynamics with remarkable precision. Juno's observations reveal complex polar cyclones, deep atmospheric flows, and previously hidden features of the planet's magnetic environment, providing critical data that refine our models of gas giant formation and behavior. Jupiter's storms, magnetic might, and intricate moon system highlight the diversity and dynamism of our solar system. Its very presence influences planetary orbits, asteroid distributions, and the long-term stability of the solar system itself. Studying Jupiter offers a window into the processes that govern not only gas giants but also exoplanets, as countless similar behemoths have been discovered around distant stars, some even more massive and exotic than Jupiter itself. Saturn, the elegant jewel of our solar system, is instantly recognizable by its magnificent ring system, a structure so vast and intricate that it has fascinated astronomers for centuries. While smaller than Jupiter, Saturn's composition, atmosphere, and rings make it a unique laboratory for understanding gas giant dynamics, planetary formation, and celestial mechanics. This planet, bathed in sunlight and adorned with ethereal rings, represents both beauty and immense scientific intrigue. Saturn formed approximately 4.5 billion years ago in the cooler outer reaches of the solar nebula. Its gravity enabled it to accumulate vast quantities of hydrogen and helium, creating a massive gaseous envelope surrounding a core of rock, ice, and metals. Unlike terrestrial planets, Saturn lacks a solid surface as we know it. Descending into the planet's atmosphere gradually transitions from gaseous hydrogen to liquid metallic hydrogen under extreme pressures. These layers, in combination with rapid rotation, completing a rotation in just over 10 hours, create dramatic atmospheric phenomena and a flattened oblate shape. The most iconic feature of Saturn is its ring system, composed of countless particles ranging from tiny dust grains to enormous boulders. These rings are primarily made of water ice with traces of rock and organic compounds. Their origin remains a subject of scientific debate. Some theories suggest they are remnants of a shattered moon, while others propose they formed from primordial material that never coalesced into a satellite. Regardless of origin, the rings are extraordinarily thin, typically only tens of meters thick, yet extend hundreds of thousands of kilometers in diameter, creating a celestial display of unparalleled grandeur. Saturn's atmosphere is a realm of stunning dynamics. Bands of clouds, like those on Jupiter, swirl in alternating patterns, driven by winds exceeding 1,800 kilometers per hour at the equator. Massive storms, sometimes forming hexagonal patterns at the poles, demonstrate the complex interplay of atmospheric currents, rotation, and thermal gradients. These storms, along with lightning events, release enormous amounts of energy, revealing the power of weather in a giant, gaseous environment. Saturn's magnetic field, though weaker than Jupiter's, is still incredibly strong, generated by metallic hydrogen currents within the planet's interior. This magnetic environment traps charged particles, producing radiation belts and influencing interactions with the planet's moons. Speaking of moons, Saturn boasts over 80 known satellites, each with unique features and scientific significance. Titan, the largest moon, has a dense, nitrogen-rich atmosphere, rivers and lakes of liquid methane, and a surface sculpted by wind and precipitation, making it one of the most Earth-like environments beyond our planet. Enceladus, a smaller icy moon, ejects plumes of water vapor and organic compounds from its south polar geysers, hinting at subsurface oceans that could harbor microbial life. The discovery and study of Saturn have been revolutionized by spacecraft missions, most notably Cassini-Huygens, which orbited the planet from 2004 to 2017. Cassini provided detailed maps of the rings, observed seasonal changes, measured atmospheric compositions, and delivered the Huygens probe to Titan's surface, revealing landscapes of frozen methane rivers and icy plains. These observations transformed Saturn from a distant point of light into a dynamic, multi-layered planetary system with ongoing geological and atmospheric processes. Saturn's rings are not merely static. They exhibit waves, gaps, and resonances caused by gravitational interactions with moons. Phenomena such as the Ink and Keeler gaps, maintained by shepherd moons, demonstrate the intricate dance of gravity and motion at work. These dynamic interactions offer a natural laboratory for understanding disk physics, which is applicable to protoplanetary disks and the formation of planets around other stars. The planet's influence extends beyond its immediate environment. Saturn's gravitational presence stabilizes certain regions of the solar system, shepherds asteroids into resonant orbits, and interacts with the solar wind, creating unique auroral displays at its poles. Studying these interactions sheds light on the broader mechanics of planetary systems and the balance required to maintain orbital harmony. Saturn embodies a blend of elegance and raw power, from the icy brilliance of its rings to the turbulent storms of its atmosphere. Its moons, magnetic environment, and intricate ring dynamics make it not only a visual spectacle, but also a cornerstone for understanding gas giant formation and evolution across the cosmos. Saturn remains a symbol of the solar system's complexity, beauty, and enduring mysteries waiting to be unraveled. Neptune, the distant blue giant of our solar system, exists at the very edge of the Sun's influence, a world shrouded in mystery, extreme winds, and deep, turbulent clouds. Its striking azure color, first noted through telescopic observation, conceals a complex interior and dynamic atmosphere, making Neptune a fascinating subject for planetary science and a gateway to understanding ice giants, both in our solar system and beyond. Formed approximately 4.5 billion years ago, Neptune occupies the outermost region of the planetary disk. Unlike Jupiter and Saturn, which are primarily composed of hydrogen and helium, Neptune contains a higher proportion of gases, water, ammonia, and methane mixed with hydrogen and helium. This composition classifies it as an ice giant, a distinct category that differentiates it from the gas giants of the solar system. These ices, under immense pressure, form supercritical fluids and contribute to the planet's unique magnetic field and internal heat dynamics. Neptune's atmosphere is a turbulent and fast-moving domain. Winds on Neptune are the most extreme in the solar system, reaching speeds of up to 2,100 kilometers per hour. These supersonic winds drive massive storm systems, some visible as dark spots, reminiscent of Jupiter's Great Red Spot. Observations from the Voyager 2 flyby in 1989 revealed the Great Dark Spot, a storm system comparable in size to Earth, moving across the planet's southern hemisphere with immense energy and speed. Neptune's clouds, composed of methane ice crystals, produce striking bands and streaks that highlight the contrast between deep blues and lighter azure hues, a visual testament to its atmospheric dynamics. Despite its distance from the Sun, Neptune radiates more heat than it receives. This internal heat, generated from residual formation energy and slow gravitational contraction, drives convection currents in the atmosphere, fueling storms, cloud formation, and the planet's dynamic weather patterns. The combination of intense internal heat and supersonic winds makes Neptune a laboratory for extreme meteorology, challenging our understanding of atmospheric physics in low solar flux environments. Neptune's magnetic field is both unusual and fascinating. Tilted at 47 degrees relative to its rotation axis and offset from the planet's center, it produces a highly asymmetric magnetosphere. This magnetic geometry interacts with the solar wind in unpredictable ways, shaping auroras and influencing the behavior of charged particles around the planet. These magnetic phenomena are crucial for understanding how ice giants generate magnetic fields differently from terrestrial planets and gas giants. The planet is accompanied by 14 known moons, with Triton being the largest and most intriguing. Triton is unique among large moons because it orbits Neptune in a retrograde direction, suggesting it was captured rather than formed in situ. Its icy surface, active geysers, and nitrogen-rich thin atmosphere make it a captivating world for studying cryovolcanism and geological activity at extreme distances from the Sun. Triton may also hold clues to the formation and evolution of Kuiper belt objects and the outer solar system. Neptune's rings, though faint and narrow compared to Saturn's, contribute to the planet's complexity. Comprised of dark, dust-like material, the rings are structured by gravitational interactions with small moons, creating arcs and gaps that reveal the dynamic processes shaping ring systems. Studying Neptune's rings provides insights into the evolution of planetary ring structures across the solar system and the gravitational interplay between moons and rings. Exploration of Neptune has been limited, with Voyager providing the most detailed observations to date. Yet the data collected has revolutionized our understanding of ice giants, revealing a world of extreme winds, turbulent storms, unique magnetic geometry, and complex interactions between moons and rings. Future missions are proposed to further investigate Neptune's atmosphere, magnetic field, and Triton, potentially unlocking secrets of planetary formation and habitability in the outer solar system. Neptune stands as a testament to the diversity of planetary environments. Its violent winds, deep blue clouds, internal heat, and icy composition contrast sharply with the familiar terrestrial planets, offering a glimpse into the extremes of planetary physics. By studying Neptune, scientists gain a comparative perspective on planetary formation, atmospheric dynamics, and the processes that govern ice giants both within our solar system and around distant stars. Uranus, the ice giant, with a strikingly tilted axis, is one of the most mysterious and least understood planets in our solar system. Unlike any other planet, it rotates almost on its side, with an axial tilt of approximately 98 degrees. This extreme orientation gives rise to unique seasonal patterns, unparalleled among the planets, and has puzzled astronomers since its discovery in 1781 by William Herschel. Uranus' distinct tilt, icy composition, and subtle blue-green hue create a world that is both fascinating and enigmatic, offering profound insights into planetary formation and dynamics. Formed over 4.5 billion years ago in the outer reaches of the protoplanetary disk, Uranus' composition differs significantly from Jupiter and Saturn. It is classified as an ice giant, composed primarily of water, ammonia, and methane ices, with a relatively thin layer of hydrogen and helium enveloping a dense, rocky core. This mixture of ices under immense pressure leads to exotic states of matter, including supersonic water, which exhibits properties of both a solid and a fluid. These extreme internal conditions contribute to Uranus' faint internal heat, which is surprisingly low compared to Neptune, raising intriguing questions about its thermal evolution. Uranus' axial tilt is perhaps its most defining feature. This sideways rotation results in extreme seasonal variations, with each pole experiencing 42 years of continuous sunlight followed by 42 years of darkness. These unusual seasons profoundly influence atmospheric circulation, cloud patterns, and weather phenomena, creating a climate unlike any other planet in the solar system. The reasons behind Uranus' tilt are thought to involve a colossal impact early in its history, potentially caused by a massive protoplanet or multiple smaller collisions which knocked the planet onto its side. The atmosphere of Uranus is composed mainly of hydrogen and helium, with traces of methane giving the planet its distinctive cyan blue color. Methane absorbs red light, reflecting the blue and green wavelengths back to observers on Earth. Although less visually striking than Jupiter or Saturn, Uranus' atmosphere hosts dynamic clouds, storms, and jet streams that evolve over time, influenced by seasonal shifts and internal heat flux. Observations from the Hubble Space Telescope and past spacecraft have revealed subtle, bright cloud features, suggesting localized upwelling of methane-rich air and complex atmospheric dynamics. Uranus possesses a magnetic field unlike any other planet. It is significantly tilted relative to the planet's rotation axis and offset from the center, creating an irregular and asymmetrical magnetosphere. This magnetic peculiarity affects the behavior of charged particles, auroras, and interactions with the solar wind, challenging traditional models of planetary dynamos and highlighting the diversity of magnetic field generation in ice giants. The planet is encircled by a system of narrow, faint rings composed of dark, rocky particles. Discovered in 1977, these rings are less prominent than Saturn's, but equally intriguing, providing insight into ring dynamics, satellite interactions, and the processes that sculpt planetary debris over billions of years. Uranus also hosts 27 known moons, including Miranda, Ariel, Umbriel, Titania, and Oberon. Miranda, in particular, presents a geological mosaic of cliffs, canyons, and terraced formations, evidence of past tectonic and possibly cryovolcanic activity, suggesting that even distant planets can harbor complex geological processes. Exploration of Uranus remains limited, with only a single flyby by Voyager 2 in 1986, which provided critical data on its atmosphere, rings, moons, and magnetic field. This encounter revealed the planet's icy composition, subtle cloud bands, and extreme tilt, but many questions remain unanswered. Scientists continue to propose missions to study Uranus in detail, seeking to uncover the mysteries of its internal structure, atmospheric behavior, and potential for harboring subsurface oceans within its moons. Uranus represents the extremes of planetary diversity. Its sideways rotation, icy interior, faint internal heat, unusual magnetosphere, and satellite system make it a compelling subject for understanding ice giants, both in our solar system and in exoplanetary systems. By studying Uranus, researchers hope to unravel the processes that govern planetary tilts, magnetic field generation, and atmospheric dynamics in environments far removed from the warmth of the sun. Meteors and asteroid belt. In the vast expanse of our solar system, beyond the comforting warmth of the sun, lies a realm both mysterious and violent, a realm where celestial travelers hurtle through space at unimaginable speeds. These travelers are meteors, streaks of light that illuminate our night skies, yet carry within them the history of our universe. To understand these fleeting sparks, one must first understand their origins, their journeys, and the cosmic forces that sculpt their paths across the heavens. Meteors are fragments of matter, remnants from the early solar system, traveling at speeds that can exceed 70 kilometers per second. Each meteor begins as a piece of rock or metal, often a fragment of an asteroid that has broken free from the gravitational pull of its parent body. When these fragments enter Earth's atmosphere, friction causes them to burn, creating the spectacular streaks of light visible from the surface of our planet. To the human eye, they seem instantaneous, almost magical, yet each meteor carries the story of billions of years, a record of processes that shaped not just our solar system, but the very planet we inhabit. The origins of meteors are intricately linked to the asteroid belt, a vast ring of rocky bodies orbiting the Sun between Mars and Jupiter. This belt is a relic of the early solar system, a collection of material that never coalesced into a planet due to the immense gravitational influence of Jupiter. Each asteroid in this belt is unique, with its own composition, history, and internal structure. Some are rich in metals, remnants of planetary cores that failed to form, while others are composed primarily of silicate rock, holding clues to the primordial materials from which the planets themselves were born. Through the lens of modern astronomy, the asteroid belt is more than a collection of rocks. It is a cosmic archive. By studying the composition of these asteroids, scientists can trace back the chemical processes that occurred during the earliest stages of the solar system. Carbonaceous asteroids, for instance, contain organic compounds, complex molecules that may have been the seeds for life on Earth. Metallic asteroids, by contrast, tell the tale of planetary differentiation, the process by which heavier elements sank to form cores, while lighter silicates formed crusts. Every fragment, whether it ends up colliding with another asteroid or falling as a meteor to Earth, is a messenger from a time before life existed on our planet. The relationship between meteors and the asteroid belt is profound. The belt acts as a reservoir of potential meteors, a chaotic dance of colliding bodies whose interactions send fragments spiraling into the inner solar system. Some meteors are tiny, mere grains of sand burning up high in Earth's atmosphere. Others are colossal, capable of causing mass extinctions, altering the course of evolution itself. The famous Chicxulub impactor, which struck Earth 66 million years ago and contributed to the demise of the dinosaurs, is a stark reminder of the power these celestial bodies can wield. But meteors are not just agents of destruction. They are also carriers of creation. Many scientists believe that water and organic molecules were delivered to Earth via meteorites, those meteors that survive the fiery descent and reach the surface. This celestial delivery system may have been critical in shaping the conditions necessary for life to emerge, seeding our planet with the ingredients for oceans, atmosphere, and eventually living organisms. Each time we witness a meteor streak across the night sky, we are glimpsing a fragment of the universe's own history, a momentary connection between the present and the deep past. Observation and research have revealed the incredible diversity of meteors. Some display brilliant colors as different metals and minerals ionize in the atmosphere: copper producing green streaks, sodium creating yellow glows, and iron adding fiery orange hues. Others are accompanied by sonic booms or explosive fragmentation, phenomena that scientists meticulously record to understand the structure and composition of the meteor. Technological advancements, from radar tracking to satellite monitoring, have allowed us to map the trajectories of potentially hazardous objects, deepening our understanding of how the asteroid belt continues to influence Earth's environment. Asteroids themselves are dynamic collisions within the belt. The belt is not a calm, static collection, but a living system of gravity, momentum, and impact. Over billions of years, these interactions have shaped the architecture of our solar system, influencing planetary orbits, sculpting rings, and even contributing to the formation of moons. For instance, some theories suggest that the moon itself may bear evidence of early asteroid impacts, the remnants of violent collisions captured in its pockmarked surface. Moreover, the study of meteors and the asteroid belt informs our search for resources beyond Earth. Asteroids contain precious metals, rare elements, and volatiles that could fuel future space exploration. Understanding their composition and behavior is critical not only for planetary defense, but also for envisioning humanity's expansion into the cosmos. Every meteor, whether tiny or immense, carries lessons about chemistry, physics, and the delicate balance of forces that govern celestial mechanics. In conclusion, meteors and the asteroid belt represent more than objects in space. They are chapters in the epic story of our solar system. They remind us of the violent, chaotic, yet beautiful processes that have shaped the cosmos. They challenge us to look beyond our terrestrial perspective, to appreciate the scale of time and space, and to understand that Earth itself is a participant in a much larger cosmic narrative. Each streak of light across the sky is both an ending and a beginning, a fiery descent that connects us to the vast ancient universe, and an invitation to explore, understand, and marvel at the forces that brought us into existence.